now. It'll be a few seconds. Okay, I think we're live now. So welcome everybody to today's quantum discussion. Our guest today is Rob Spekkens, who is a senior researcher in quantum foundations at the Perimeter Institute. So hi, Rob.
Hey, Matt.
I have to say this discussion is going to be, it's a little bit awkward compared to the other ones because I know Rob really well. Rob is to some extent sort of a mentor of mine, even though we're really contemporaries. Everything I learned about, basically everything I learned about quantum foundations that I'm not confused about and that I'm correct about is really due to Rob, whereas everything that I'm confused and wrong about is my own fault. So Rob is something of the guru of quantum foundations for me, so we agree on a lot of stuff. But I hope we're going to find some things that we can discuss that we disagree on. So anyway, welcome, Rob, and I hope this is going to be a good discussion.
Yeah, in my experience, we always find things to disagree about. So
yeah, well, everything. Being an academic is about finding things to disagree about anyway. So I wanted to start. So some of our viewers will have seen our earlier discussions with Sean Carroll and with Travis Norson. So we've talked already a little bit about things like the measurement problem and the many worlds and the de Broglie-Bohm interpretation. So I think that you're in the same camp as me, that when it comes to the interpretation of quantum mechanics, you believe the correct interpretation out of the ones we have so far is none of the above. Am I?
Yeah,
so,
yeah. Yeah.
So what I'd like to ask you to do first, if you can, is sort of explain why. So can you explain why you think none of the interpretations that we have so far are going to be correct, and also what you see as the main problem with our understanding of quantum mechanics as it stands?
Yeah. So maybe to start, I guess maybe all these conversations sort of start off by assuming that you want a realist interpretation rather than just a purely operational one. So I'm definitely in the camp of people who want realism. And so part of our discussion today will be about, what does that mean to sort of want realism in quantum theory?
So just to interrupt, just to interrupt here to explain what that means. I mean, the way I normally formulate it is to say that there's some real world out there independent of us, and our job as physicists is to attempt to describe that world. Would you agree with that kind of characterization?
Yes, to some extent, like that's a good place to start. But I think part of the challenge of actually achieving a satisfactory realism in quantum theory is to figure out exactly what about our kind of classical notions of realism have to change to sort of accommodate a realist interpretation of quantum theory. So often people talk about picturability, and maybe implicitly some people think that there's somehow that the realist interpretation of quantum theory should get you back to something that's a little bit more classical. For my part, where I've kind of landed on this is that for me the essence of realism is going to be providing causal explanations of statistical correlations. So if you've just got a theory that tells you what sorts of statistical correlations to expect, to my mind, you don't have realism because you don't know whether those correlations are by virtue of a cause-effect relation or a common cause or some combination. So one of the minimal criteria for realism, in my view, is to have satisfactory causal explanations of the correlations that the theory predicts.
Okay, so I mean, I think we're going to spend a lot of time talking about causality and cause and effect a bit later on. So maybe we can say a little bit about what you think is wrong with the standard approaches to realist interpretation.
Okay, so when I was doing my Ph.D., I spent a lot of time sort of learning about various different interpretations of quantum theory, became very familiar with all of them. And I mean, they all had problems that were sort of individual to those interpretations, I would say. But moreover, none of them really struck me as particularly satisfactory in the sense that you you expected that I expect at least that the correct interpretation would kind of make quantum theory seem, more natural, that it would sort of offer some kind of like satisfactory intuitions about what's going on and explanations of what's happening, and it would somehow reduce some of the mystery and make more sense of quantum theory. So in that sense, I think I started, not really being in any particular camp, basically, as you say, sort of not really endorsing them, but hoping for some other option. And then I got wind of, the idea that the quantum state was more analogous to a probability distribution in a classical theory. So quantum state could be more analogous to a specification of the relative probabilities of different classical states than it was analogous to a particular physical classical state, if you're making an analogy between quantum and classical. So
Yeah.
I
think we might need a little bit of elaboration here for some of the viewers.
Yep.
I mean, let me try. So, if you think about a coin, flipping a coin, once you flip the coin and you're holding it under your hand, it's either heads or tails, right? So it has a definite state of, either being heads or being tails, but you don't know it. Whereas if you flip the coin and you don't look at it, you might say that there's a 50% probability of it being heads and a 50% probability of it being tails. That's not really a property of the coin, it's a property of what you know about the coin. So what you're trying to say here is that we should think of the states, what's normally thought of as the physical state in quantum mechanics, as being something more like that 50-50 distribution representing our knowledge than it is like the definite heads or the definite tails.
Yeah, the analogy I like to use when I give public talks about this is if you have like a billboard in some language you don't understand and it's got numbers on it, then those numbers could represent properties about the weather. If it's like a weather prediction, so like some number might be the temperature, some number might be the wind speed that day, but the probability of rain, it is not like that. There's no property you can find on a given day that corresponds to 0.5, if 0.5 is the probability that the weather person assigned to it raining. And so those different numbers on the billboard really represent two different things. One would be like a property of the weather, and the other would be a property of or somebody's quantification of their degrees of belief about what the weather is going to be. And so the question is, does the quantum state, which is a number of real parameters, should I think of those parameters as representing properties, or should I think of them as representing degrees of belief about those properties? And so, yeah, so I originally, that this was a kind of new idea to me, but I eventually, warmed to it, and I thought that the analogy was incredibly strong, and that all the standard interpretational strategies didn't really offer much of an explanation of why you had this really nice analogy. And this ultimately led me to come up with this, I called it toy theory, where you could essentially start from an axiom, a principle that maybe the world is just like classical physics, but there's a fundamental constraint on how much you can know. So there's a limitation on what any agent in the world could possibly know about the physical states of systems. And I was able to show that just starting from, if you formalize that in a particular way, you could derive something that looked very much like the formalism of quantum theory, that reproduced a lot of the phenomena in quantum theory that people took to be sort of intrinsically quantum. So, things like this Einstein-Podolsky steering phenomena, where, when you do a measurement on this particle, which was entangled with some other particle, you can update the wave function of the distance particles in different ways depending on what you measured here. That comes out in this approach as just a kind of updating of your knowledge. You can refine your ignorance about the distant system in many different ways depending on what properties you've chose to measure on the other system that was correlated with it. So I think that was one of the first examples I worked out. But then you can easily show that it reproduces the fact that there are measurements in quantum theory that you can't measure simultaneously. The teleportation protocol, something called the no cloning theorem, all these things about quantum theory that people typically point to as being mysterious and non-classical arise in this kind of approach. And the only difference from a classical theory is that it's stipulated that you can't know everything. So the kind of success of that, at being able to reproduce certain parts of quantum theory persuaded me that there was something really right about this analogy between that quantum states are representing degrees of belief or degrees of knowledge rather than reality directly. And partly because I hadn't put it in; it all come out of this axiom that you can very much derive certain parts of the quantum formalism just starting from this axiom, rather than it's not really an interpretive program in a way. It's sort of reconstructing some part of the formalism from that. So I found that very persuasive. But you only get a subset of quantum theory this way, and there's certain phenomena that quantum theory predicts that you can't reproduce, like the phenomena or the experimental correlations that are associated to something called Bell's theorem and the Cauchy-Spectre theorem, which we're probably going to talk about. But these are sort of two big results in the foundations of quantum mechanics. Sort of maybe the best known no-go theorems. They sort of stipulate interpretational strategies that don't work. So these approaches, like allowing the quantum state to be understood as just being about knowledge, doesn't help you understand these sorts of phenomena. So from that point onwards, the research program was really, shift your attention to those phenomena. So people sometimes refer to Bell's theorem as being about non-locality. Cauchy-Spectre is about contextuality. So the lesson of all that was one should focus on those phenomena and phenomena like no cloning and wave particle duality and teleportation and things like that, which I could capture in these models, were sort of less informative as clues for how to move forward. And the program became, look, the framework in which those no-go theorems, Bell and Cauchy-Spectre are phrased, is the problem, in my view, that the quantum state should still represent knowledge, but it's not knowledge about variables that take on one of a set of values. And secondly, the knowledge is not represented in the usual way that you would classically by probability distributions. So the program became, can you find a kind of alternative to these what we call the ontological models framework, which sort of stipulates how the reality should be represented mathematically and how our knowledge of reality should be represented mathematically. Can you find an alternative to that within which you can make sense of quantum theory and within which the quantum state is just about knowledge?
Okay, so there was a lot there. So I think we need to break things down a little bit. We had I had talked with Travis Norson in one of the previous videos a lot about Bell's theorem and non-locality. So we don't have to go into many details, but I believe that sort of these days you now have sort of a unifying idea for what these sort of problematic aspects of these traditional realist models are, which you call Leibnizianity.
Right.
So perhaps you'd like to try and give an explanation of what that is and how that encompasses these results about Bell's theorem and Cauchy-Spectre and things like that. Okay, well, let's. In my view, Leibnizianity is covering more the contextuality, Cauchy-Spectre side of things. Okay, we could have a different discussion about Bell, but let's see. So maybe the place to start would be just to say a little bit about what the Cauchy-Spectre theorem says and what it has to do with Leibniz. So the Cauchy-Spectre theorem articulates a principle of non-contextuality. So they're looking at whether you can understand quantum measurements and quantum experiments in terms of sort of an underlying classical theory where systems really have properties and measurements are really just revealing something about those properties. And when you prepare something to feed into the measurement device, that's generally represented by just sort of sampling from the possible properties the system has. So you could probabilistically sample the physical state of the system from among all its physical states, and then you might get some probability distribution over measurement outcomes if those measurements reveal something about the properties. But the constraint of non-contextuality is the following: that in quantum theory, there's often incompatible measurements. So position and momentum cannot be measured simultaneously, or spin along the z-axis and spin along the x-axis cannot be measured simultaneously.
And so what you can have is situations where I might have three different types of measurements, say A, B, and C, and B and C are incompatible. You can't measure them at the same time. But A and B can be measured at the same time, and A and C can be measured at the same time. And so when you want to measure A, you have this choice of measuring it with B or with C. And so let's say you measure A with B, and then you should forget what the outcome of the B measurement was and just record the outcome of the A measurement. So the idea of non-contextuality is that the A measurement is measuring the properties of the system, and it's measuring the same properties regardless of whether it's being measured together with B or together with C. That's the idea. And so at first you might say, well, that seems like a strong assumption, and why would you think that? Why couldn't it measure different properties if it's, definitely there's different devices being used to measure A in these two different contexts. So you might say, well, why not? Why should it be represented the same way? And the answer is that the distribution over outcomes of your A measurement turns out to be exactly the same regardless of which context you're implementing it in. So imagine you measure A with B, you set up a preparation device, and then you measure A together with B. You forget the B outcome, you look at the A outcome, you do this many times, and you get a particular distribution over the outcomes of your A measurement. Now you do the same thing with this other device, which measures A together with C, and you find you get exactly the same distribution. And then you try a new preparation, and you get exactly the same distribution. And for every preparation you do, you find that the distribution over the outcomes of the A measurement in these two cases is exactly the same. So that's pretty striking that they look the same from the perspective of this sort of input-output functionality. No matter what I feed into it, I get the same sorts of experimental statistics. And so the best explanation, you might say, of that is if they're measuring exactly the same properties. The alternative is that maybe these two devices are measuring different properties, but none of the preparations sample the physical state in a way that you can see that difference. So the alternative is this very conspiratorial notion that there's differences in what's going on in reality, but they never get manifest at the operational level in terms of these measurement outcomes. So that when I started thinking about non-contextuality, that struck me as sort of the key aspect of it. And so this led to a kind of generalization of the notion to lots of different devices, and that's where the connection to Leibniz comes in. Kai, did you want to?
Yeah, there are some questions in the audience. So generally, people are asking if you can explain how superpositions and maybe things like interference work in the ignorance-based explanation of quantum mechanics that you were talking about a little while ago. So if you can just explain a little bit more about that interpretation of that theory, I think that'll address several questions.
So it was superposition, and what was the other?
Interference.
Interference. Okay. Okay, let me try superposition. So if you so often people talk about the trouble with trying to interpret quantum states as being merely about degrees of knowledge, is that it seems like any kind of sum of two quantum states would have to represent what's called a convex mixture. So where something like if I flip a coin and I prepare this one if I get heads, and I prepare this one if I get tails, that's called a convex mixture. And you find that if you try to interpret superposition in that way, it really doesn't work. But in this sort of approach where quantum states represent states of knowledge, and they're always incomplete states of knowledge, so there's always something left to be known. So in the simplest example, you've got 4 physical states, and you could have knowledge that it's one of these two, or you could have knowledge that it's one of those two, or your knowledge could be this, or this, or these two, or these two. So you have sort of 6 states of maximal knowledge. And what you find in that context is that if you ask, can I build a new valid state of knowledge out of, say, this state of knowledge and this one, it's one of these two or one of these two, the answer is yes. I could sort of take one of the physical states from this guy and one of the physical states from this guy and combine them into a new state of knowledge, a uniform probability distribution over these two. So there's sort of a notion of combining these maximal states of knowledge to get new ones. And there's many possibilities. I could combine this pair and this pair to get this pair, or this pair, or this, or this. And that corresponds to the kind of relative phases that appear in these superpositions. So there's sort of a natural way of understanding what a superposition can be. For interference, it's a bit trickier. I mean, there's a long story, but roughly speaking, if you think about Feynman's puzzle, so Feynman said, okay, say we have a double slit experiment. Imagine the particle really did go through one of the slits. Well, okay, sorry, the double slit experiment is puzzling because if you don't look which slit the particle went through, you get interference on the screen. And if you do try to look and see which one it went through, the interference goes away. So Feynman's puzzle is this: if there's really sort of some matter of fact about where the particle went, which slit it went through, then if it made it to the screen, let's say I block one of the slits so that at the screen I don't see interference. If it made it to the screen, so it went through the slit that was unblocked, how did it know whether the other slit was blocked or not? If the other slit was blocked, it can go essentially anywhere on the screen, whereas if the other slit is unblocked, it's supposed to exhibit an interference pattern. So there's some places on the screen it's not allowed to go, but it went through the top slit. How did it know what was going on at the other slit? So that's the kind of puzzle that Feynman set up. And in these sorts of approaches, the resolution of these sorts of puzzles is that in quantum theory, we assign a vacuum state. And people often will think about the quantum state corresponding to the vacuum as sort of just, nothing there. But if you take the idea that quantum states are always representing incomplete knowledge of some deeper reality, then even the quantum vacuum state represents knowledge of some deeper reality. And so you've kind of got 2 degrees of freedom. You've got is the particle, here, or is this region of space sort of excited and containing a particle or not? But regardless of whether it contains a particle or not, it also has a kind of phase degree of freedom. And so even on the path where the particle didn't go, there's a phase degree of freedom. And that phase degree of freedom, if the slit is unblocked, it doesn't get randomized, and that is what determines the interference pattern. And if the slit is blocked, it gets randomized. And so there's still sort of these local degrees of freedom, and you can explain the phenomenology. And in retrospect, what sort of appears mysterious about it is the fact that you have to, or what made it seem mysterious was thinking that the quantum vacuum was sort of nothingness that could not possibly transmit information. Anyways, I obviously there's much more I could say about that explanation, but that's the short version.
Yeah, this is the subject of a long-awaited paper that we're supposed to be writing.
Yes.
Anyway, so hopefully that will clarify the issue. Did you have you had another question you wanted to bring in, Kai? Okay. Yeah, so I suppose, so where we're getting to here is that these kind of theorems like contextuality, the way you view them is that they're indicating that there's something wrong with our underlying framework that we normally use to talk about realist theories. So I want to get on to talking about what you think the replacement is. But before we do that, I don't want to have a long discussion about this, but we should probably mention the Pussy-Barrett-Rudolph theorem, which was an attempt to sort of directly rule out this kind of interpretation. So maybe you could just spend a couple of minutes talking about that, if you or saying why that hasn't changed your mind.
Right. That's also the subject of the paper that we're not writing together, but I'm writing, which has yet, been waiting for years to come out. But so let's see. So let me put it this way: it seems to me that the standard way people interpret the PBR theorem and its assumptions actually makes a kind of ironic mistake. So let me tell you what I mean by that. In the context of Bell's theorem, I think there's sort of an ironic mistake that often gets made. So the history of Bell's theorem is, Einstein essentially showed that if you treat the quantum state as describing reality, meaning that you can't vary the quantum state without varying, the reality. That's what the quantum state represents, a property of the system. He showed that if you have that sort of interpretation of the quantum state, then you have to have non-locality. Okay, so he showed this in 1935. And in fact, if you ask, well, what if the quantum state represents the only reality, then he showed that that would imply non-locality even way back in something like 1927. So sort of, we knew very early on that if you take that interpretation of quantum state, then you can't have locality. And that's really why Einstein favored a kind of interpretation of the quantum state as representing knowledge. But then Bell in 1964 showed that even if you allow the quantum state to represent knowledge, you still can't preserve locality, within this usual framework that uses, classical variables and classical probability theory. So what was hard to do was to rule it out for the cases where quantum states were states of knowledge. So the ironic mistake is to look at Bell's theorem and say, oh, clearly that shows that you should have just taken the quantum state to represent a complete description of reality. You would sort of be mistaken, because Bell's theorem shows you have to have no locality regardless of how you interpret the quantum state. But it would be ironic because you've gone back to the position that's actually easy to rule out, the one that we already knew was not on the table in 1927. And so I think there's something similar that happens with PBR, that if you take the assumptions of PBR, what they look like is an assumption of what I'll call separability, so that the physical state of a composite can just be given in terms of the physical states of each of the components, and a notion that if I have a product quantum state, then it should be represented by a product distribution. So the distribution over the hidden states should also factorize. So if you take those as the two assumptions, then you find that you can rule out not just these models where the quantum state represents knowledge, but you also rule out the ones where the quantum state represents reality as well. And in fact, you can do it trivially, because as soon as you allow for entangled states, you can see that violates this assumption of separability. An entangled state can't be written down as just specifying some quantum state for one part and some quantum state for the other part. So from my perspective, this kind of standard view of things, which is just it assumes separability and this property of factorization, that just to think that endorses quantum states as representing reality is to make an ironic mistake. The detailed assumptions, I think the assumptions that allow you to salvage the quantum state as a state of reality are unnatural. They're not assuming this separability. So the separability is basically saying there's no holistic properties. If you give me a composite system, I can just reduce its properties to the properties of the components. But if you don't assume that, but instead you say, oh no, there are sometimes holistic properties when there are entangled states. Then we have holistic properties. And we have product states, we have no holistic properties. So I like to call that the entanglement holism link. So if you endorse that whenever you have entangled states, you need holistic properties, then you can rule out the quantum state as being a state of knowledge. But the problem is that this assumption is not natural to somebody who buys into the quantum state as a state of knowledge. I think it's natural to the people who think the quantum state represents reality, because for them, entanglement is a kind of species of strange holistic properties. But in my toy models where there's a restriction on how much you know, all entanglement is correlation. And so the assumption of the PBR theorem, to my mind, is very unnatural for somebody who's pursuing this quantum states as states of knowledge type of research program.
So, I mean, you're really saying it gives an unfair advantage to the interpretations in which the quantum state is real at the outset.
Well, I'm not saying it's an unfair advantage. I'm saying it's circular in a way. Like if you're going to try to make a no-go theorem for a particular interpretational point of view, you have to start with assumptions that are acceptable to that point of view. If you want to say, I want to try to persuade you to believe that the quantum state's real, here are my assumptions. They're reasonable if you think the quantum state's real. Like that. How do we get off the ground with that kind of argument? You can't. So yeah, I think the assumptions ultimately are circular. And the assumptions that are not circular, like separability, they just rule out both the quantum state being real or a state of knowledge in this framework of ontological models. So personally, I think the PBR construction is just a nice proof, like Bell's theorem, like the quotient spectre theorem, which shows that there's something wrong with this framework, that regardless of whether we take the quantum state to be representing reality or a knowledge of reality, something about the framework of ontological models is not right, and we can't reproduce the quantum predictions with it.
Okay. I could push on this point further, but I think I'd like to move on to, I guess, more recent stuff. So, and also to what the solutions to all of these problems might be. So you mentioned earlier that you think that the key factor of a realist interpretation is having a causal understanding of correlations. So, so we're going to start to talk about causality. When physicists start to talk about causality, it often gets a little bit confused because there are various things that go under that name. So I'd like to do a little bit of disambiguation at the beginning. There's at least three things that physicists mean when they talk about causality. One is the structure of space and time, space-time as we learn from Einstein's relativity, which has to do with the fact that there isn't an absolute time that applies to all observers, if you like, and the fact that there's a limit to the speed with which a signal can be sent, and so that there are certain things that given an event, something happening at a particular time, there's certain things which are definitely in its future, certain things that are definitely in its past, and then there are certain things that are neither in its future nor in its past, and that there's a structure of that on space and time. So that's sort of relativistic causality, if you like. There's also what you might call the arrow of time that gets talked about quite a lot. The fact that there seems to be a definite direction to time. The future is different from the past. We remember the past and not the future. Time seems to only flow in one direction. And most physicists adopt the view that this has something to do with thermodynamics. It has to do with there being special initial conditions at the beginning of the universe that made things behave like this. And then thirdly, there is sort of our ordinary everyday notion of cause and effect, if you like. When I say something like, the goal was scored because I kicked the football in the right direction. That's our sort of ordinary everyday notion of cause and effect. And indeed, that notion of cause and effect is a very important one for science, because you want to be able to say things like administering this drug caused the patient to get better, right? You want to be able to draw conclusions like that. So I would say, and I think one of the points we're going to end up disagreeing on is, the extent to which these different notions of causality are more fundamental than one another, and the extent to which they can solve, any of them can solve the problems of quantum foundations. But I think, there has been, I would say that there's a bit of a sort of causal revolution in quantum foundations going on, where people have been taking seriously this idea of cause and effect and how to understand it in quantum mechanics. So perhaps you can say a little bit about that and how you think that can give us an interpretation of quantum mechanics that is realist in a suitable sense.
Okay, good. So I think maybe the right place to start is to talk about kind of a revolution that's going on outside of physics, but in the field of statistics and machine learning. So there's a nice parallel, actually, I think, between disputes in the foundations of quantum mechanics and disputes in statistics. That just as in quantum theory, for a long time, most physicists were wedded to a view that the business of the theory is to just kind of make predictions, and all your concepts somehow should be defined in terms of experiments you might do, and maybe just the kind of statistical data you get out of your experiments. Similarly, in statistics, for a long time, there was a taboo against talking about cause and effect at all. That was considered sort of unprofessional. But in recent years, people have developed a formalism for talking about cause and effect in a totally classical context. And there sort of, I guess maybe it's worth saying a little bit about the kinds of distinctions there are between correlations and causation. So the example I like is, just if you want to say, what's the difference between correlation and causation? Here's a correlation, the rooster crowing and the sun rising. What does it mean for them to be correlated? It means that I can make inferences about one if I learn about the other. So it's a symmetric relationship. If I, hear the rooster crowing with the blinds shut, I can infer the sun is rising. And if I read in the almanac that the sun will rise at 7 a.m. tomorrow, then I can infer that that's when the rooster is going to crow. So it goes both ways. And it's about updating your knowledge about one variable by learning about another variable. That's correlation. Whereas causation is about, can I change the value of one variable by manipulating the other variable? So in the case of the rooster and the sun, you say, well, if I make the rooster crow in the middle of the night, does it cause the sun to rise? No. But if I make the sun rise early for the rooster, perhaps by moving the rooster towards the east, then the rooster does crow early. So that's the causal relation. It's asymmetric, and it's about changing one thing based on another. So what we often have in statistics is statistical data that exhibits correlations, but it's not obvious whether those correlations are due to cause effect, and maybe it's not obvious what direction the causal arrow is. In the example I just gave, it was obvious. There are examples where it's not obvious whether it's a cause effect or a common cause. So that my favorite example there is there's a correlation between how many firefighters showed up to fight a fire and how much damage was done. That's a positive correlation, and the explanation is that the larger the fire, then the more firefighters the dispatcher sends, and the more damage that gets done. So there's a common cause that explains positive correlation. It's not because the firefighters are so inept that sending more of them causes more damage. So in all these situations when you're just given the correlations, that doesn't tell you immediately what the causal structure is and what the causal explanation is. And so this framework that has been developed in this field that is now called causal inference, led by people like Judea Pearl, it's about trying to extract from some statistical data what are the possible causal explanations of that data. And so that has provided a kind of language for talking about cause and effect, and a formalism that I think was absent previously. And when you sort of take that formalism over and say, what if I try to cast quantum theory into that kind of formalism? So in particular, you can ask, what about these no-go theorems, which are really about providing a kind of ontological model, trying to make sense of quantum theory in terms of classical variables and probability distributions of those classical variables. You can ask that same question in this new framework, and for me, it really works extremely well. It's extremely well suited to the problems of quantum theory. For me, for a long time, I've really bought into Jaynes's. So E.T. Jaynes, the physicist, has this nice quote about the problems with quantum theory. It goes something like, the current formulation of quantum theory is this curious mixture, in parts about reality and in part about incomplete human information about reality, all scrambled up by Bohr and Heisenberg into an omelet that no one has seen how to unscramble. But we have to unscramble it, otherwise we don't even know what we're talking about. So that's been my kind of guiding philosophy for a long time, that we need to disentangle what in the formalism is about reality and what's about our knowledge of reality. And distinguishing correlation from causation is a kind of example of that. And so this framework that's been developed by the people in the field of causal inference provides a really good beginning to trying to tease apart those different notions of cause-effect relations versus just mere correlation. So like in a Bell experiment, where you have these entangled particles and then measurements, you can ask a question like, do I see the correlations because there's a cause-effect influence between, say, my choice of measurement here and the outcomes I get over here? Or is it just a common cause explanation? And so, like this framework can allow you to sort of address those sorts of questions. And I wrote a paper with the master's students, Chris Wood, many years ago, as you know, Matt, which sort of looked at Bell's theorem kind of from this perspective of causal modeling. And to me, it clarified a lot of things that you could think of Bell's theorem as basically saying, suppose you demand that you explain correlations causally. And then you make one other assumption, which is that those explanations shouldn't be fine-tuned, which in this formal language means that so these causal models come with a causal structure. So it might say, this variable influences that variable and influences that variable, so there's like a graph of arrows between variables, what can influence what. But you also need to stipulate some parameters, which tells you how a given variable depends on its parents in that graph. And so the no fine-tuning assumption is that if you're going to try to explain some features of your statistical data, like some independences, those independences, it shouldn't hold for only very special choices of the parameters, choices of the parameters that are so special that you would have to sort of fine-tune them to get that independence to hold. Those independences that you observe should hold generically, and they should be a result of the structure itself. And so what you find when you look at the correlations that quantum theory predicts for a Bell-type experiment is that the what are called the no signaling conditions, the fact that the distribution over outcomes at one wing of the experiments doesn't change as I change the choice of measurements at the other wing. In all the kind of standard interpretations of the Bell experiment, attempts to give causal explanations of the Bell experiments, you run afoul of this no fine-tuning principle. That basically all the previous attempts to actually provide causal explanations are fine-tuned explanations. So that maybe the most popular is to say that in Bell experiments you do have causal influences from one wing going to the other wing, superluminal causal influences that explain the correlations we see. So that is an example of fine-tuning, because I need to choose the parameters carefully such that those influences don't lead to correlations that are signaling. And similarly with attempts, what are called superdeterminism, where you imagine that the common cause is of the two outcomes is correlated with one of the settings, that also is fine-tuned. And similarly with retrocausal accounts, where you imagine that there might be some causes backward in time. So all of those are fine-tuned. So you can sort of sum up Bell's theorem by saying there just is no causal explanation in this framework, classical framework of causal modeling, if you demand that your explanations should be not fine-tuned. And this is something that people in the causal inference community do demand. Like they consider any explanation that's fine-tuned to be a bad explanation, and I think rightfully so. So what it suggests is that if you want to avoid fine-tuning, then what you should do based on this no-go theorem is change one of the implicit assumptions, which is that the right framework for talking about correlation and causation is this classical causal model framework, where those hidden variables that are acting as common causes take on one of a set of values, and our knowledge of them is represented by a probability distribution. That's the opportunity to say that's not the right way to represent causal relations and our incomplete information about them. So the idea is to let's replace that framework of classical causal modeling with a different quantum framework and still secure causal explanations that are not fine-tuned.
Right. So, and you've been working on this kind of formalism as well, where you change. We sort of keep the structure of causal relations the same, but we change what theory of inference we use with it. So we use, if you like, a quantum theory of inference rather than classical probability theory to do this formalism. And in that case, you get a common cause explanation for the correlations in the Bell experiment, right? So
yes, sort of, yeah. I would say, I wouldn't quite go so far as to say, we've achieved a satisfactory causal explanation. It is true that I think you can, come up with a notion of a quantum causal model that can sort of explain the correlations we see in terms of just a common cause. But has it really offered a satisfactory causal explanation? I think we need to be careful there. And so in a recent paper that I wrote with some co-authors that came out last year, we tried to set down, what would a non-classical causal model have to look like for it to be really considered a satisfactory causal explanation. And it's not just the theory of inference that's going to have to change. It's also sort of how functional dependences work, how causal dependence works. So yes, the structure can be conservative, sort of like common causes, no superluminal causal influences, but the parameters that are used to describe causal connections are going to be different. And so you can set down a number of kind of constraints on that. And that's the parts that's missing. Can we really say that these quantum causal model formalisms can be essentially understood as arising from, a theory of causal influences and, inferences in the presence of incomplete knowledge that really satisfies a sort of enough constraints that you would want to say this is a proper explanation. So that's sort of where the work needs to be done still.
Okay, so I think we're in the last. Sorry, Kai, did you have a?
Yeah. The audience is basically just asking if you can explain what you mean by fine-tuning a little bit better, and also how retrocausal models in particular are fine-tuned.
Okay, let's see. So take an example where I have, say, 3 variables, A, B, and C, and imagine that I've got lots of, I've got A influencing B, so there's sort of an arrow from A to B, and C is a common cause of A and B. So for that kind of model, what you need to stipulate is sort of how does B depend on its parents? So B's parents are A and C. How does A depend on its parents? So A's parents are C. And C has no parents. So I need to specify a distribution over C, tell you something about the probability of different values of A given every value of C, and the probability of different values of B given every possible combination of values for A and C. Those are the parameters. And so if you write down generic values of those conditional probabilities, generically you'll find that you'll get lots of different possible distributions over A, B, and C. In fact, you can get any one of them. And most of them do not have A and B uncorrelated. A and B are typically correlated in that scenario. But you can choose very special values of those parameters that make A and B uncorrelated. So you think of it this way, you can sort of say, well, the direct connection, the cause-effect connection between A and B could make them positively correlated, and the common cause connection between A and B makes them negatively correlated, which exactly compensates the positive correlation and makes them uncorrelated. So that's how you would get sort of a factorization on lack of statistical dependence between these 2 variables by virtue of choosing the parameters very carefully. So it's a fragile thing, because if you change any of the values of those parameters even a little bit, you'll destroy that factorization. So fine-tuning in this context is saying that technically the values of the parameters have to be chosen from a set of measure 0. So if I considered a uniform probability distribution over all values of those parameters, this would be a set which had vanishing this set that achieves the independence would have vanishing probability in that set. So that's what fine-tuning is. A retrocausal model. So one of them, so here, say I have settings and outcomes on each side of the Bell experiment. I have a common cause. The idea of a retrocausal model is, let's try to avoid having causal influence go in a way that relativity finds problematic, which would be sort of, from one region to a space-like separated region. So, kind of like faster than light could possibly go. Instead, you say, well, let's keep it inside these light cones, right? So there's a light cone is sort of like all the places in the future that I could influence starting from here. And there's a backward light cone that says, here are all the places in the past that could have influenced this point. So the idea would be, well, if my influences stay inside the backward light cone, then I can sort of zigzag this way. I can sort of influence backward and then forward. And in some sense, it's sort of more, less in tension with relativity, because the influences are propagating inside light cones. And so they sort of feel more relativistic. but at the end of the day, you're still setting up a correlation between, for example, the setting on the left and the outcome on the right. So if you say that the setting on the left reaches back in time and changes the value of the hidden variables, and then that influences the outcome on the right. At the end of the day, you still have a causal pathway between that setting and that outcome. And so to explain the sort of lack of signaling, which means that, that I find the distribution of its outcome to be independent of the choice of the setting, I need to fine tune the parameters. It doesn't matter what the causal pathway is, whether it's direct, whether it first goes back, and then as long as there's a causal pathway, I've got to choose the parameters in such a way to ensure that independence.
Okay. Since we only have 10 minutes left before the Q&A session, I do want to push on some things, and maybe we'll start arguing and disagreeing about things here. So I think there's two serious issues I see with the sort of quantum causal models type of program. Let me push on what I think is the most serious one. So there's a view that, part of the point of realism is to get rid of any notion of any anthropocentric notions from physics, or at least any sort of observer-dependent notions from physics. So there's a view that says that anything to do with causality is necessarily of that type. It was the famous quote by Bertrand Russell. I pulled it up here while you were talking, just so that I could show how smart I was by quoting somebody. It says that the law of causality, I believe, like much that passed as muster among philosophers, is a relic of a bygone age, surviving like the monarchy only because it is erroneously supposed to do no harm. So, here he's referring to the fact that, you can't find any notion like causality in fundamental physics. It's just not there. So, and I would say that that sort of the conventional view among physicists is that something like causality, in the sense of cause-effect relations, is something emergent. And you can see where this comes into the type of program that you're proposing here, which is you have this notion of causality that you expressed it yourself. That's this notion of causality that's interventionist, right? So the way the reason why it's the sun that causes the rooster to crow and not the other way around is because if you change what happens to the sun, it changes what the rooster does. But if you change what the rooster's doing, it doesn't change the sun, right? So there's sort of an interventionist, to define what we mean by causality, we need the notion of an intervention. But what's an intervention? What kinds of intervention can we do? What do we think of as an intervention? To my mind, that seems to have to do with the arrow of time, another notion of causality that I was talking about earlier. So, the fact that it seems to us that we can choose the settings of measurements in quantum mechanics and only observe the outcomes, so we can intervene on measurement settings, but we cannot intervene on measurement outcomes, seems to me to be to do with the thermodynamic arrow of time. So, for example, in order to, this is the way I would express it. So in order to be able to make a setting on a measurement device, say you have a switch which can be in two different positions, what I have to be able to do is come up to that device and whatever position I find it in, make a choice to say switch it to 0. According to what we know about thermodynamics, I may not know what state the switch is in beforehand. In order to do that, there's an entropic cost. It's Landauer's erasure principle, which tells us that whenever you erase some information, you have to exchange heat with the environment. So to make that intervention, it's only possible in a universe where we have the thermodynamic arrow of time going in this direction, in the direction that we observe it in. And if we believe in the standard account that arrow of time is emergent, not a property of the fundamental physics, then it means our notion of what's an intervention is only emergent and can't really be playing a role of explaining anything at a fundamental level. So to sort of, the traditional goal of realism is to talk about the universe doing its own thing completely independently of us. Whereas here we seem to be formulating physics in terms of a notion that's fundamentally dependent on our perspective.
Okay, let me jump in. So although I did try to explain the distinction between causation and correlation in terms of an interventionist notion of causation, I don't think that is the fundamental notion of causation. So I'd say in a classical theory, I would associate causation with just functional dependence. So I would define it not in some anthropocentric way in terms of interventions, but just in terms of counterfactuals. And so a causal relation is one that allows me to say, what would have happened for every possible choice. What would happen to B for every choice of A? So B depends functionally on A. If you specify the function, you know what the value of B would be for every value of A, even though in the real world, A only takes one value. So this is completely familiar from physics, that when Galileo and Newton wrote down the first laws of physics, they were of functional form. And the beauty of it was they stipulated not just what the actual history of the universe was, but what would have happened if you went in and, not just if you went in and modified, but also if you imagine that the world had been different and A had taken a different value, it allows you to say what value B would have taken. So I think classically the right way of thinking about causation is just as functional dependence, and it's, I think, a primitive notion. It doesn't depend on agents at all. And I think the notion actually that cause-effect relations are emergent somehow, that they, the philosophers would say they supervene on facts about correlations, for example. So I think in physics and also in statistics, there is this kind of impulse to think that we will conclude that there's a cause-effect relation between A and B only if they are correlated in certain circumstances. So maybe only if by intervening on A, I can change the distribution on B, for example. That would be a purely interventionist notion. So let me explain why I think a purely interventionist notion is not the fundamental notion of causation. So it's just because of the Vernam cipher, or the one-time pad. So this is something from cryptography. You have a plain text, which is the message you want to send. You have a key. So you imagine that you have an agent in the field. You both have a copy of the key, which is just a bit string that's chosen at random and nobody else knows. And you take your plain text and you add it some mod 2, all those bits to the key, and you get the cipher text. So the idea is, like, if my message was just one bit, a 0 or 1, I would add the key, which is 0 or 1, add them. So 0 plus 0 is 0, 1 plus 1 is 0. And if they're different, I send 1. So now, in that circumstance, first, if the key was chosen completely at random, then even if I intervene on the plain text and I change the value of the plain text, the probability distribution over the values of the cipher text is exactly the same. The reason this is secure is because the probabilities for all the different possible values of the cipher text are exactly the same for all possibilities for the plain text. That's why learning cipher text teaches you nothing about what the plain text was. And so what you find is that you have no interventional notion of causality. I change the plain text, nothing happens to the cipher text. And yet clearly in this situation, we want to say the plain text influences the cipher text because the cipher text is a function of the plain text and the key. So that, to my mind, is the clearest example of how a purely interventionist notion of causation, what Pearl calls the do conditional, can't be the definition of when two things are causally connected. So it has to be, is it the case that B is ultimately a function of A? That's when B and A are causally connected. So the notion of causation I have in mind is not emergent in the sense that you described, and it's not anthropocentric either. So I don't think it's subject to these sorts of criticisms.
Okay, I mean there is a so I mean it's not interventionist, but it does depend on having a notion of counterfactual.
Yes,
would you agree with that?
Which we're already using in physics. Every time we write down a law of physics and say, I can predict the trajectory regardless of what initial conditions you care about.
Yeah.
I mean, the law of physics is something that allows inferences about counterfactuals. We've been drinking this Kool-Aid for a long time. I don't see why we should now suddenly be about counterfactuals.
I mean, I do still have a concern with that, which is that, up until now, the laws of physics have been formulated in a way, aside from some special solutions in general relativity, for instance, in such a way that you can make a division into the initial conditions and the laws, right? But part of the causal program here is it's not really like that, right? So it's there isn't a privileged role for initial conditions in this kind of framework. It's sort of just like anything else. It's the parameters of the theory, and they're subject also to causal structure. So my concern is here that it might be a little bit more deceiving to talk about counterfactuals as if they were straightforward in this kind of circumstance, right? In standard physics, we can talk about the counterfactual if the initial conditions were different and the laws were the same. Here we have to say, okay, if the value of this variable were different, and then what is the same? The causal structure.
Well, the function, I would say like a
function.
Yeah, like if you so what people in the causal inference community call a structural equation model is one where you have not just a structure, but for every dependence, like I say a variable that has a certain number of parents, you stipulate what function dictates how that variable depends on its parents. So those are the parameters, these functional dependencies, together with the values of the root variables. So I think in a structural equation model, you have exactly that same. It's essentially like if you think of a law of physics and then maybe turn it into a cellular automata. I think structural equation model is a lot like that. You instead of differential equations, you just have these discrete dynamics given by functions. And so yeah, I would say the law of physics initial conditions is like stipulating the functions in your causal model and the values of your root variables. I mean, one place I'd agree with you is it's not clear if you want to replace all that with a kind of quantum version.
Sure.
Then you're not going to have functional dependencies. You might have something different, like a unitary dependence instead, and you're certainly not going to have your variables be represented as kind of sets. But it's not clear to me that means you can't talk about counterfactuals anymore. I think the challenge is to really be able to have a notion of causation and inference that is different from the classical one, but still supports all the sort of standard concepts, like reasoning about counterfactuals and all the usual stuff about inference, like statistical independences. So you want that in your modified theory. And I mean, the image I use for this, like sometimes the objection I hear about this sort of approach is that, well, this doesn't even make sense because there's sort of analytic truths about causation and inference, right? That this is what causation is, this is what inference is. You can't change that without it no longer being about causation and inference. And my response to that is, that kind of attitude is much too conservative, and it would sort of stifle progress in physics. Because if you look at what Einstein did with the notions of space and time, after we had special relativity, our notions of space and time changed. They're still recognizably space and time, but they don't obey all the properties they did before. And so the picture for the program here is that we want a kind of a causal theory and a theory of inferences and interactions between them that satisfy a number of axioms, and that at the end of the day are still recognizably sort of about causation and inference, but that are different enough that the concept of causation and inference changes. So it's a bit like how in non-Euclidean geometry, which is the geometry that general relativity is based on, just as an area of mathematics, there's still points and lines in non-Euclidean geometries. The meaning of point and line changes by virtue of the axioms that define that geometry. So there no longer are sort of intuitive notions of points and lines, the ones that Euclid was dealing with. We change the notion of points and lines. They acquire their meaning based on the axiom system in which they're embedded. So that's the same strategy here. We'll have a kind of new axiom system for causal theories, inferential theories, and how they interact. And the meaning of causal notions and of counterfactuals, for example, and other things are going to emerge from that axiom system.
Yeah. Okay. We're going a bit over time. I do want to. I will give you the last word, but let me just, say one more thing about this. So you talked a bit about the structural equation models and functional dependence being the notion of causal structure. I have to say, I've never fully bought this part of the program. And it's partly because even if it doesn't exist, I think it should be possible to make sense of the notion of retrocausality. And this makes it sort of difficult to do that because, functional dependencies can, they can only really go in one direction, right?
Why?
So,
Why
unless you have reversible functions, but if everything's a reversible function, you'll never be able to determine what's cause and what's effect.
I don't follow that. Like if I have a variable that's at this point in time and I stipulate that its causal parents are things that are earlier, but also some things that are later than it.
Right.
And then I say it's the way it depends on them is some function. Then I feel like I've encoded retrocausation. That the causal relations are stipulated by the functional dependencies. And they could potentially fail to respect the spatio-temporal locations of these objects. I mean, personally, I'm not inclined to endorse retrocausation because I don't think one needs it. And so I would rather have notions of space-time separation kind of emerge from causal notions. Like the causal notions are more primitive and the spatial temporal notions sort of derive from them. But I mean, if you want to pursue a retrocausal approach, I think these structural equation models can still be accommodated to that kind of program.
Okay, I won't push on this further here because otherwise, and we could talk about this for hours probably, and I'd like to do that at some point. However, I don't want to completely bore our audience, and I know we have plenty of questions from the audience, so let's move on. So thank you very much, Rob. And let's move on to the audience Q&A. So Kai, would you like to bring in some questions from the audience?
Yeah, I'll try to go roughly in order. So we have one, if the PBR theorem can be bypassed, then are there any models like your toy model that explain more or all quantum phenomena? That was a question from quite a while ago, but there was no good time to ask it.
So I think maybe the best way to answer this question is that the PBR theorem is maybe best understood in a context of a kind of different research program from the one I've been trying to describe. So you might have wondered whether you could have a kind of classical theory and a classical theory of incomplete knowledge of those variables and still reproduce quantum theory, right? So even prior to the PBR theorem, you had Bell's theorem, you had quotient spectre. So you know that any such attempt is going to have to do some, things that are contextual. It has to have contextuality hardwired in. It has to have superluminal influences, for example, or superdeterminism, these fine-tuned things. So you might say, oh, okay, well, I'll deal with all that. And I just want to know if I could make such a theory work where quantum states are now, representing states of incomplete knowledge rather than reality. And so that's kind of the place where the PBR theorem lives. It's a sort of a question of whether you can do this. But to my mind, it's not the interesting question, because I think we already knew that it was this framework of ontological model that was the problem. And what was elegant about and natural about the explanations that the toy theory and theories where you have a restriction on how much you know, was that they were satisfying this assumption of non-contextuality, and they were achieving it all with very conservative causal structures and no superluminal causation. And so, yeah, to my mind, a invariable model that takes the quantum state to be partly about knowledge, but still has all this, fine-tuning and contextuality is just as unpalatable as a model that takes the quantum state to be real. There is a question of whether it can be done, which is sort of an academic question, but I don't think it's the important question. I can't remember if there's another part to the question, but I think I might have answered it.
I think you covered it. So another question we have, I'm actually not going to do them in order because there are two that I'll say which are going to probably require longer answers. So this was towards the end. Jane's response to Bell's theorem was that the conditioning on a distant event doesn't imply causation, so you don't have to use separable probabilities. Is this refuted by causal models?
I think, so I'm not totally familiar with what James said about Bell's theorem, but my impression is that James just didn't actually appreciate Bell's theorem. So I think James misunderstood Bell's theorem. He thought that you could, try to explain the sorts of correlations you saw in a Bell experiment as being by virtue of a common cause. Like he essentially, I think, was thinking the same way Einstein was thinking. That maybe this collapse of the wave function at a distant location is just an updating of one's knowledge. But Bell, showed that sort of interpretation won't work. If you want to make something like that work, you're going to have to move outside of this framework of ontological models, change the kind of framework you're using to describe causal relations and inference in the kinds of ways we've been talking about. And I didn't see anything like that suggestion in James. So I think James was just mistaken in his comments on Bell's theorem.
All right, so now one of the questions that may require a longer answer. What do you think about Sabine Hostenfelder's recent claims that superdeterminism is not fine-tuned? Have you seen that paper? Do you have any opinions on that?
I haven't seen that paper, so I couldn't say. Maybe I will say that I think the notion of fine-tuning that people in the causal inference community use, I think it has some problems. I think that there are ways in which you could have a fine-tuned model that I would say doesn't make the explanation unnatural. So for example, a thermal distribution is a kind of point in the space of all possible distributions, but it's a special one. It's sort of the end product of a thermalization process. And so if you've got a model that requires very particular choices of the parameters, but you can prove that those parameter choices are, for example, the result of an equilibration process, then I think that makes the model more compelling, and you can say there's a sense in which that sort of fine-tuning is not so bad. And I think there are approaches that are kind of like that. So I would say Antoni Valentini's variant of Bohmian mechanics, where he imagines that so in Bohmian mechanics you have a distribution over particle positions, which is usually specified by the wave function. He imagines it could be different from what's specified by the wave function. And so and he shows that there's a kind of equilibration process. So I think the kind of explanation he gets for why we don't see signaling is a kind of fine-tuning that has an explanation. However, his model also implies that if you chose different values of those parameters, and he thinks you can find those, then you should be able to show that relativity is wrong and really signal faster than the speed of light. So it's that part of his program which I feel it makes it not my favorite approach, because I think relativity is going to be preserved. But all this to say, I think you can get around this fine-tuning argument in certain respects. But I think ultimately all these types of explanations, superdeterminism, superluminal causation, retrocausation, they do all still have a kind of problem that the sort of causal explanation they offer is not very satisfactory. And so there's a paper that we're going to put out soon where we did an experiment, a Bell type experiment, and we used standard model selection tools to try to adjudicate between different causal explanations of the correlations we saw. So one model would be this quantum causal model that we talked a little bit about, where it's just a common cause, but the parameters in the model are kind of radical. They're not just conditional probabilities. And then another model we looked at is one where the parameters are conservative, right? They're just conditional probabilities, but the causal structure is radical. It's like a superluminal influence from the setting on one side to the outcome on the other. And then another model we look at would be this superdeterministic one. And so we do the standard thing where you take sort of half your data, you train the parameters of your model based on half the data, and then you see how well it predicts the other half of the data, right? So you find your best fit parameters from some of the data, and then you say how well does it predict the rest, and then you score the models based on which ones have more predictive power. And so what's nice about this is that usually we sort of compare models based on whether they can make the data look likely. So we're saying it's fine as long as it doesn't underfit the data. But a more methodologically sound approach would be to say, let's make sure it doesn't underfit the data, and let's make sure it doesn't overfit the data, right? So if you give me a bunch of data points, I might be able to fit very closely to those points by choosing some curve with a lot of parameters in it. But I'm just fitting to noise, and so I'm going to do a very poor job of predicting some future data. And so that's what we essentially see, that these models that have this radical causal structure, what seems to be happening is that the data you get from the experiment, which is a finite sample, has some kind of what looks like signaling, that the distribution over an outcome on one wing is slightly different for different values of the settings. And these models look at that and they think it's a real feature. They don't see it as a statistical fluctuation. They encode a functional dependence from one wing on that setting variable. And then when it comes time to predict the rest of the data, they do a bad job. Whereas the quantum causal model never has that dependence because it's all common cause. So when you fit the parameters, you sort of have to interpret those dependencies as fluctuations. So all this to say that there's sort of other ways of thinking about the fine-tuning argument, which I think are more methodologically sound, like these standard model selection techniques, and they generate the same kinds of conclusions.
All right, so this next one I'm just going to read because it's sort of an open-ended question about your epistemic models. So if our existing framework of quantum mechanics merely describes our knowledge of the state, what's actually going on? That's a big one. And then maybe we don't know because there are limits to knowledge, but doesn't that mean our knowledge, or at least information, is in some sense real, such that there are physical trade-offs for gaining it?
Don't think can you repeat that last bit?
So the last bit is, doesn't that mean that our knowledge, or at least information, is in some sense, quote, real, such that there are physical trade-offs to gaining it? I'm not entirely sure I know what the question is, but I figured I would read it as it was.
Okay, so for the first part of the question, I mean, although there are some people who endorse a view that somehow quantum theory is all about information, and information is somehow a natural kind. I mean, the view that I espouse is that this distinction between what's real and what we know about it, you can't talk about knowledge without talking about sort of what is knowledge about. So there's definitely going to be a kind of reality, and the quantum state is a knowledge about that reality. So it really is very similar to this kind of hidden variable perspective, where there's properties of a system and your knowledge is about those properties, with the difference being that we want to leave the sort of classical notion of properties behind and sort of replace it with a kind of more exotic notion of causal relations and inference. But it's definitely not knowledge about, say, the outcomes of future experiments or some operational proxy for reality. It's meant to be knowledge of reality. So to say that the quantum state is about knowledge, it is not to say we're done, now we understand quantum theory. This what I'm describing is a research program that isn't complete yet, which is trying to come up with an interpretation of quantum mechanics wherein the quantum state is merely knowledge of some reality, but there's also a description of that reality. So that's definitely part of the objective of the program, is to describe that reality. Now, does knowledge become sort of kind of reality itself? I mean, there's a sense in which any agent in the universe having knowledge about something, well, there's some reality corresponding to the agent's memory and maybe the agent's brain, and so there's some sense in which sort of that knowledge gets encoded in physical degrees of freedom. But nonetheless, I mean, I think there's an important distinction. Maybe the one thing I would say is that a constraint on any kind of alternative view of causation and inference, like having a non-classical notion of causation and inference, which is to the classical notions as non-Euclidean geometry is to Euclidean geometry. Anything like that, I think, will have to satisfy a kind of consistency relation, that in the following sense that, what is a theory of inference? Okay, how do I think about that as a physicist? What is a theory of inference? I mean, I would say that a theory of inference should be thought of as like an adaptation. So as an agent, one needs to survive in the world, make good choices. A theory of inference helps you do that. It helps you survive. And that's why your theory of inference shouldn't be independent of the laws of physics, because it's trying to help you survive in a world that's governed by a certain set of laws. So if you ask, what's the most adaptive theory of inference to use in a given world, it could very well change, as you change the laws of physics, the best theories of inference can change. So classical probability theory may be adaptive in a world of classical physics. But if I imagine a world with a more exotic, non-classical type of causal, set of causal dependencies, the most adaptive theory of inference, will be different from classical probability theory. So maybe that's one sense in which the theory of inference is kind of locked to the theory of the world.
All right, last but not least, we've been talking about interventions and states of knowledge. What do you have to say about consciousness?
Not sure we have enough time to deal with that question.
Well,
You could just say nothing.
so I guess in this point of view, I mean, there are some people who think that consciousness, might help us solve the problems of quantum theory, that somehow collapse of the wave function is a genuine physical event, and it's only when the wave function gets coupled to something that has consciousness that those collapses occur. And certainly that's no part of the view that I'm describing here, that agents are just collections of atoms like anything else. Consciousness doesn't have anything specific to add to quantum theory. We don't need a theory of consciousness to help solve the problems of quantum theory in this point of view. I mean, maybe one thing I would say is that we left the topic of Leibniz abruptly a long time ago, but let me just bring it back to try to and connect it up to this question. So we talked about how non-contextuality was an example wherein you assume that if you can't tell a difference at the operational empirical level, then you shouldn't assume that there's any different at the ontological level. So Leibniz had this principle called the identity of indiscernibles. And he had different versions of this principle, but if you look at the one in his debates with Newton, so there's something called the Clarke-Leibniz correspondence, where Leibniz sending letters to Clarke was basically a proxy for Newton, and they were debating about absolute space. Leibniz basically makes an argument that says, if you have things that are empirically indistinguishable, then they should be ontologically identical. I think his argument fits that pattern well. And his original argument was, if you take the Newtonian universe and you move all the particles over by 5 feet, nothing you could observe would change. And then Leibniz says, look, so the kind of ontology that Newton's positing says that there's changes that you can make that would lead to just no consequences in principle, by the lights of the theory itself, no consequences to these changes. From Leibniz's point of view, that's not a change in the physical reality. If it doesn't lead to any consequences observationally, even in principle, then it's really the same reality. And the only thing that's important is the relative positions of these particles, not their position in absolute space. So this Leibnizian principle, the ontological identity of empirical indiscernibles, is not really something that physicists talk about. But when you look at the work of Einstein and how he came to special and general relativity, Leibniz's principle is the key in my view. So, for example, in his 1905 paper, which introduced special relativity, he basically attacked the then prevailing ether theory. So people had this idea that there was this all-pervading ether, and light was an oscillation in this medium of the ether. And Einstein said, look, here are two situations which, by the lights of that theory, are physically different. One would be a magnet which is moving with respect to the ether, and a coil that's stationary with respect to the ether. So the magnet moving through the coil. And the other would be the magnet stationary with respect to the ether and the coil's moving. And in both cases, you get a current in the coil, but the explanations are very different. In the first case, you have the electrons in the coil seeing because they're moving, they see this magnetic field from the magnet, but they're moving through it, and so they feel a Lorentz force. That's what it's called when a moving charge sees a magnetic field. And in the other case, you have the magnet's moving, so you have this time-varying magnetic field, which is an electric field, and so now the electron feels this electric force to the electric field. And Einstein points out, but the currents we see are exactly the same. There's no way of telling which of these two scenarios are in, even in principle, according to the theory. So Einstein says, so obviously, you know, the fact that we have these two different physical situations by the lights of the ether theory that are totally indistinguishable means it's bad, and we should replace it with a notion of what's going on, which cares only about the relative motion. And anyway, so that's like one version of it. But if you look at the equivalence principle in general relativity, it's exactly the same pattern. He's basically saying, let's throw out any pictures of what's going on physically that suggest that there could be, you know, different physical scenarios corresponding to exactly the same observable phenomena, and replace them with an explanation such that, you know, any difference in the physics leads to, in principle, observational differences. So anyway, so that's kind of why I think that physicists should basically look at Leibniz's principle and be sort of singing his praises and saying, like, has there ever been a principle in physics that's had more success than Leibniz's principle? It's right there, you know, in the relativity revolution. And that's why I think non-contextuality is a good principle and something we should try to preserve in an interpretation of quantum theory. And that's why we should reject this framework. Consciousness, you know, there's a lot of people who suggest that, you know, maybe there's such a thing as an organism that it behaves just like us, you know, and yet doesn't have the kind of zing of consciousness. You know, there's nobody home. I think these are called zombies in the philosophical literature. Leibniz's principle would say any idea that there could be sort of a difference between, you know, like individuals who have the zing of consciousness and those who don't, and yet there be no observational difference, even in principle, is running afoul of Leibniz's principle. And so we should reject those kinds of theories of consciousness. So there's the connection for you. Leibniz's principle will tell you why certain theories of consciousness are objectionable.
There's an observable difference to the zombie, though. In principle.
Maybe. I don't know. It depends. Is the zombie thinking it's conscious as an automaton? Anyway, there were no more questions from the audience, so we can wrap it up here unless anyone wants to throw one in. There's a little bit of a lag, so we can wait and see if we get one, but we could also just wrap it up.
Okay, well, while we're waiting for that, and we are close to time anyway, I want to thank Rob again for joining us today, spending his time with us. I want to encourage everybody who's watching this now to tell all of their friends, relatives, acquaintances, enemies to watch this video. And also I want to mention that we have another discussion lined up for next month on March the 24th. Same time, I'll be talking to Chandra Prescott-Weinstein about her new book, The Disordered Cosmos, and that should be a good discussion as well, so I hope you'll be able to join us for that. Were there any other questions, Kai? In that case...
well, thanks, Matt. This was a lot of fun.
Yeah, thank you very much, Rob. And I'll end the stream now. And thanks everyone for joining us. Okay, we are done.